All right. Seems like everyone's checked in. Couple of things we're going to do today. We're going to review a little bit about what arithmetic sequences actually are, some of the notation with them, and then some questions over W11, and then we'll go into geometric sequences. All right. We're really only covering two different types of sequences, and that's arithmetic and geometric. So after this geometric part is over, we'll actually start to get into more interesting like probability and stuff. So if you think this stuff is like really easy, or even you're a little bit confused about it, don't panic just yet, because we're gonna get into some more interesting stuff that isn't super dependent on this. Like of course these are the ground rules for everything we're gonna be doing coming up, but it's not kind of like the end all be all. So if you're really struggling with this stuff, that's okay for now at least. It does take practice. It's a lot of like experiential kind of a thing. Um, so just kind of keep that in mind. All right. Before we get into any questions over W11, which it doesn't seem like people are asking anything specific, uh, I just want to review what we did last week. So last week we went over kind of the basis of sequences and series, summation notation, and last class we went over arithmetic sequences. So a sequence where every term you're just adding some constant is called arithmetic. Okay, so the difference between each term is the same throughout the entire sequence, and that is called the common difference. Okay, and that's really important with arithmetic sequences. Okay, there is a definite rule in order to find the nth term of an arithmetic sequence, which is written right here. Okay, you won't normally see it written like that. Like you're not just going to be explicitly given this directly this equation. It'll probably be more written like, well, it's something that looks like that. Um, Obviously, the d's will be numbers, and a1 is a number, so they'll simplify even more than that. But that is the rule in order to find the nth term of an arithmetic sequence. Okay, and the sum of a finite arithmetic sequence is this equation right here. So the sum of the first n terms is the number of terms you're summing divided by 2 times the first term and the last term that you're summing. Okay, and again, we kind of talked about that. Basically, you're just taking the average of the first and last terms and then multiplying that by however many times you're doing that. Um, that's ultimately what it boils down to. So I want to pause for a second and give people maybe a quick second or two to ask any questions about W11. Otherwise, we're going to keep going. So I'll pause it for a second. If you do have any questions for W11, this is a great time to ask. Yeah. Could you use the sum formula on an example? Yes. Can you do an example with n equals 0? Those are the ones. Yeah, we'll do both of those. So let me set that up real quick. So this problem, this is taken directly from IXL. This is at 65. Okay, so if you were struggling, this chances are this is about when you would start to. Okay, n is equal to 0 in this case. 43 is the upper limit, and we have this equation for our nth term. Okay, so the first thing we need to do is we need to find the first term. In this case, our first term is actually the 0 term because that's where we're starting to sum. So the first thing we need to do is plug in 0 into all of this. So we need to find a0, where a1, that really just means the first thing that you're summing. It doesn't necessarily always mean when you plug in n is equal to 1. It means the first term. Okay, so when we do that, we get 7 times 0 plus 3. That's just equal to 3. And then we need to find the nth term. So we need to find 7 times 43 plus 43 plus 3. Just when you do that, get 304. And then we need to ask ourselves, so we found the first term and the nth term. And then we need to ask ourselves how many terms there actually are. And it seems like there's just 43, but we start at 0. Okay, so if we just think about it on a number line for a second, right, if we start at 1 and go to 43, we know there are 43 terms in there. But instead we start at 0, which means there's one more. So n in this case is 44. So then we just plug all that in. So the sum of the first 44 terms from 0 to 43 is equal to 44 over 2 times 3 plus 304. And we do that math. To get 6,754. So while I think when people get an equation, they just think it's plug and chug. In this, you actually do have to think about it, because you have to think about what the actual first term is, how many terms you're actually summing, and interpreting that. And sometimes that's a little bit, it's not necessarily harder, it just takes a little bit of thought. So don't go into this thinking that you can just plug in 1 and then the last number and then you're done. It's not always that easy. And this is a perfect example of it. So when n is equal to 0, it's not necessarily just the upper limit, that's the number of terms you're dealing with. Where did the 44 come from? So in this equation, what this is really saying is that we want to sum some number of terms, all right? And this n, that's not just the upper limit. Okay, that's the number of terms you're actually summing. So we got 44, kind of from our number line, right? So if we went from the first, so from 1 to 43, that's 43 terms. But because we start one term back at 0, that's actually 44 terms. So that's where that came from. Again, think of it as you're taking the average of every term and then adding that together the number of times you're summing it. Okay, so it has to do a lot with how many terms you're actually summing. So that's the part we got to be careful with. Okay, are there any other questions over this problem? And I know I keep saying this. Calculus looks a lot like this, right? So in calculus, you're going to start taking integrals from like 0 to some number, and then it'll throw in integrals from negative some number to positive some number. And you got to think about how many times you're summing something. Okay, so this is, I know it seems like kind of simple on just adding a bunch of things together, uh, but stuff that you're doing in this chapter is very much reflected into stuff that you're going to do next year in calculus. So this stuff is, it's not necessarily like super important, but it's very much the basics of what you're going to be doing in a couple of months. All right. So let's go on to geometric sequences. And I don't think I put in your homework yet. Your homework is just that next IXL. I think it's W12. And that will only be the case if we get to where I want to get to. So I will let you know if that's actually the homework. But that's what it will be if we get to where I want to get to. All right, so let me get back to today. And before I kind of scroll down, we need to absolutely know this equation, the nth term of an arithmetic sequence, and we very much need to know the sum of a finite arithmetic sequence. Okay, and there's going to be a lot of different types of these. All right, so there's these two for arithmetic, and then there's actually three for geometric. Two, hopefully, we're going to get to today. So there's going to be an nth term equation and a finite equation, and then we'll eventually get to an infinite equation and what all that actually means. Okay, but those are two equations that you absolutely need to know. And while it's probably tempting not to memorize it, I would. Obviously, when you're doing like homework and stuff like that, it's okay to have it out in front of you, but the better you know it, the better off you'll be. Okay, so let's move into what a geometric sequence actually is. Uh, in an arithmetic sequence, we were just adding some number over and over and over again. In a geometric sequence, we're not adding anymore, we're just multiplying now. Okay, so a sequence is geometric if the ratios of consecutive terms are the same. All right, and I'll get to where this means multiplication here in a second, but kind of like in order to find the common difference, we subtracted consecutive terms. In geometric, we're just dividing. So a2 over a1 is equal to a3, or sorry, a3 over a2, which is also equal to a4 over a3, and all those things are equal to one number. And that number is r, which is called the common ratio. So again, arithmetic sequences had a common difference. Geometric sequences have a common ratio. And I'll give you a second to write. And obviously, if there are any questions, go ahead and ask. Okay. Um, so like what we did with our, pretty much everything we're going to do today is very reflective of what we did in arithmetic sequences. So the first step is just determining whether or not something is actually geometric. Okay. And on the bottom of your screen, there are two sequences, and I want to focus on the top one first. And the first thing that you should do with this sequence is just take a step back and look at it as a whole, right? And you should notice that every time you move forward one term, you're doubling the last. Okay, so 2 times 2, that's 4. 2 times 4, that's 8. 8 times 2, that's 16, and so on. Okay, so if you were to kind of follow this rule, this common ratio rule, you would have 4 over 2. And if this is geometric, that should be equal to 8 over 4, which should be equal to 16 over 8, which should be equal to 32 over 16, and so on, right? And that's all going to be equal to just 2. So that's our common ratio, and because that exists, we know that this sequence is geometric. All right, so again, back when it was arithmetic, we'd be subtracting all those terms, and if it was all the same difference, there would be a common difference, and it'd be arithmetic. It's kind of the same thing. And then for this next example, it's a little bit harder to kind of see what's going on. And when there are fractions in sequences like this, it's good to look at both the numerator and the denominator, and not necessarily worry about sign or anything like that just right off the bat. But if we just look at the numerator, it's always constant. It's always just 1, so we don't really have to worry about it. In the denominator, though, different things are happening, right? So in order to get from 3 to 9, we have to multiply by 3. In order to get from 9 to 27, we have to multiply by 3. 27 to 81, we have to multiply by 3. Okay, so it seems like there's a geometric relationship. And quickly, I want to go over actually finding the ratio. So by definition, you would have 1/9 divided by -1/3. And that should be equal to -1 over 27 divided by 1/9. And that should be equal to 1 over 81 divided by -1 over 27. Now, this is where a lot of people panic because it's fractions within fractions. You guys should be decently prepared for this. But when you're dividing by a fraction, you're really multiplying by its reciprocal. Okay? So I'm just going to take this one right here. That's really equal to 1/9 times -3 over 1. Which, if you do that, ends up being -1/3. Okay, I'll just tell you that this is geometric, and all of those fractions are going to be the same, with our common ratio being -1/3. So are there questions about that part right there? And before we move on, I want you to take a quick note of these two sequences to kind of get the difference between common ratios. Okay, so in this top sequence, this 2, 4, 8, 16, 32, our common ratio is 2, and in the bottom sequence, -1/3, 1/9, -1 over 27, our common ratio is -1/3. that's going to be very important later on, because when you have a common ratio greater than 1, or the absolute value of 1, uh, it diverges. It's what it called diverges, which means there's no sum that can capture the infinite sum of that sequence. Okay. And then on the bottom, when something is between 0 and 1, it's always decreasing. It's always getting smaller, which means the sum of that infinite series, if that series were to keep going, actually does converge to something. Okay, and you don't need to know that like right off the bat, right this second. But there are two different types of common ratios. There's common ratios that are greater than the absolute value of 1. And there are common ratios between the absolute value, the absolute value of the common ratio is between 0 and 1. Okay, and they're two very different things. One is constantly getting bigger, and one is constantly getting smaller. Okay, which you can kind of see in both of these sequences. Okay, if we keep going, just like the arithmetic sequence, we do have a rule. The nth term of a geometric sequence is always going to be the first term of the geometric sequence times the common ratio to the power of n minus 1. And again, this is an equation that you should absolutely know. So if we were to write the sequence that we did up above, this 2, 4, 8, 16, 32 sequence, we know our common ratio is 2. And our first term of our sequence is also 2. Right, so if we were to rewrite this equation, an would equal 2 times 2 to the power of n minus 1. And if we were to rewrite that green sequence, again, negative 1/3, that's our first term. Our common ratio was negative 1/3. We could rewrite it as the nth term is equal to negative 1/3 times negative 1/3 to the power of n minus 1. Okay, so what this means, and this is kind of a different way of looking at these sequences, our first term is never multiplied by anything. It's just the first term. It's a constant. And we can rewrite the sequence as multiplying by r several different times, right? So our second term is the first term times r. Our third term is the first term times r squared. Our fourth term is the first term times r cubed, and so on. And while this may seem like it may not seem like there's a reason that I'm doing this right now, um, this is exactly how a probability distribution works. Right? You're multiplying things over and over and over again in order to get the total probability of something actually happening. Okay, so again, I want to pause there. Are there any questions over what you see on your screen? So then we'll do some examples. Um, First 5 terms of the geometric sequence. So we want the first 5 terms of a geometric sequence whose first term is 3 and whose common ratio is 2. Okay, so again, we're given exactly what we need because we know that an, the nth term of any geometric sequence, is the first term times the common ratio to the power of n minus 1. So all we really have to do is just substitute, where the first term is 3 and the common ratio is 2. So the nth term, the first term is 3, common ratio is 2, and then this n minus 1 stays there. So that's the rule, and we want the first 5 terms. Okay, so the first term again is just 3. The second term would be 3 times 2. The third term would be 3 times 2 squared. And then cubed. And then to the fourth. Questions about that example? All right, and then that second example, find the 12th term of the geometric sequence 5, 15, and 45. We have to do a little bit more groundwork, right? So we know A1 is just 5, but we need to find the common ratio. Okay, and we're told that it's geometric, so we really only need to check one of them. So we'll check these first two. So R should equal 15 over 5, which is just equal to 3. And then we can plug that into our equation. and then just plug in for 12. Plug that into our calculator, and then get an answer. So again, questions on that example? And then kind of taking this to the next step, if we're not given the first term and we're not given a common ratio, but we want to find some other term, again, the groundwork that we have to do just kind of expands a little bit. All right, so we're given the fourth term and the 10th term, and we know that it's geometric. Okay, so A4, that's 125. A10, that's 125 over 64. And then we're trying to find A14. And we know it's geometric, so we know it has a common ratio. Now, this may seem a little bit difficult at first, but the great thing about geometric sequences is that they can actually start at any time. Okay, so A4 we can actually take as A1. So we can rewrite the 10th term as kind of a function of the fourth, right? Because our fourth term is now our first. And I'm going off of this equation. And I want you to look kind of closely at this part right here, because this is where people can get this wrong, and this is where people kind of got confused on the summation stuff too. We need to think about how many times we're multiplying our common ratio by our first term in order to get to the 10th term. Okay, and we're going to do that 6 times. We're going to multiply our common ratio 6 times together in order to get to the 10th term from the fourth term. So this isn't just n minus 1 anymore. This has to be 6. All right, and then we can plug in what we know. All right, so A10, that's 125 over 64. A4, it's 125 And then we have r to the 6th power. And then we have to solve for r to the 6th. So we divide both sides by 125. And when we do that, we're just left with 1 over 64. And then we have 1 over 64 is equal to r to the 6th. Which, again, you can solve this in a lot of different ways. You could do the logs. You could take the 6th root of this. This will end up being r is equal to -2. Sorry, not -2. One half. So our common ratio, and I'll let you guys kind of ask questions about that because I realize that can be confusing. But our common ratio will end up being 1/2. And now we're just left with one unknown, and that's A14, which we can kind of just write the same equation again. Okay, so A14 will equal, and we can start at A10, times our common ratio. And then in this time, our power will be to the 4th, because we had to multiply our common ratio 4 times more in order to get from 10 to 14. And then again, we just plug in. And when we do that, we get 125 over 1024. Okay, because I want to pause there because I'm guessing there's questions over that because I skipped a couple of steps that were maybe a little bit more, maybe a little bit less like intuitive than what you're thinking. Okay, so if you have questions, please ask them. So now we want the sum of finite geometric sequences. So what we just did is we found the rule for them, and we did that in a couple of different scenarios. And now we want to find the sum of a finite geometric sequence. And before we do that, I want you to think about the sum of an infinite geometric sequence. If you took our sequence that was defined by these numbers, and you added that up to infinity, you would just get an infinitely big number because you're constantly multiplying, that's making it bigger. Okay. So right now we're going to focus on a finite geometric sequence. We're going to focus on a sequence like this that stops at some number. All right. So we're focused right now on a sequence that stops at the nth term. And we have this sum, right, in summation notation. So we're talking about the nth partial sum from I is equal to 1 up until the nth term of our geometric sequence. And this will end up being our first term times 1 minus our common ratio to the nth power divided by 1 minus our common ratio. And there is a proof to this. We can look at it a little bit later, but for now I just want you to know that this equation is super important because that tells you, again, the finite sum of a geometric sequence. So now let's do an example. All right, so we want to find the 12th partial sum of the geometric sequence given by 4 times 0.3 to the power of I minus 1. And again, a lot of this is just tracking down numbers and then plugging numbers in, and maybe a little bit of interpretation. All right. So the first thing we have to do is find the first term. All right, we have to find A1. So in order to do that, you just plug in 1 or your lower index into your equation. And this will end up being just 4. Our common ratio in this case is 0.3. And then really we have all we need, right? The only thing that you need to maybe be aware of is this n right here. And kind of like arithmetic sequences, this isn't necessarily your upper index. It's the number of terms you're multiplying together. It's the number of terms you're summing. So in this case, we start at 1, we go until n. So n is okay. But if it started at like -3 or something and went up to n, we'd have to change that just a little bit. Okay, but for now, we're okay. So our sum will be equal to so we want the 12th partial sum is equal to 4, our A1, 1 minus our common ratio to the power of 12 over 1 minus our common ratio. And for this, you end up getting a decimal, which is equal to 5.714. And then there's numbers after that don't stop. But for now, that's okay. Okay. So questions about this example? Okay, and the last bit I want to go over is the sum of an infinite geometric sequence. All right, so again, I told you to kind of start to think about the difference in common ratios. So there can be common ratios that are greater than 1 and common ratios that are between 0 and 1, or at least the absolute values of the common ratios. Okay, when common ratios are bigger than 1, the series just continues to grow, right? There's no stop to it. It just grows boundless because you're constantly multiplying by some constant that makes the next number bigger. But, and we can't sum that, right? We can't sum that because it just keeps going up to infinity. But if our common ratio is less than 1, if our absolute value of our common ratio is less than 1, the number doesn't get bigger anymore, it gets smaller because you're constantly multiplying something by a fraction between 0 and 1, right? You're constantly cutting off pieces of the last one in order to get smaller and smaller and smaller. Those type of geometric sequences we can sum, okay? So this is only true when our common ratio, or the absolute value of our common ratio, is between 0 and 1, okay? So in order to sum this geometric sequence, right, we have an infinite geometric sequence. So our upper term is is infinity. And in this case, we're actually starting at the 0 term. In order to sum this, when r is less than 1, this converges to the first term divided by 1 minus the common ratio. And again, this is a very important sum. And this doesn't just show up here. It doesn't just show up in probability. It'll show up in calculus. And it can make your life a whole lot easier in anything you do in math later on. So for example, and we'll just do one of these and then you guys can get to work. If we have the infinite sum of 4 times 0.6 to the nth power, and I want to have that sum, again, this is really just about tracking down certain numbers and then plugging them into that equation that's boxed. Okay, so define the zero term, we just plug in 0. And then the common ratio in this case is just 0.6. We carry out that math. No, I did this just a little bit wrong. So I found the zero term, not the first term. All right. And this is where this stuff gets a little bit confusing. This A1 here is there for a reason. Even though it starts at the zero term, this A1 here is there for a reason. Okay, so we still need to find A1. And then 4 times 0.6. No, I did it right in this first place. Sorry, I was looking at a different example. My bad. I've been really confusing people. So we still find A0. So ignore what I said just before. And then when we do that, we get 4 over 0.4, which is just equal to 10. Okay, so I probably confused people a little bit. We'll do another example here in a second. But I want you to think about this, all right? We just summed something that is infinite, which means it does not stop, into one number. Okay, so if we did this series, right, we'd start at 4, we'd go to 2.4, then we'd keep going down, but we never actually hit 0. Okay, and we summed that entire thing up until infinity into one single number, which is exactly what you're going to be doing in probability, and that's exactly what you're going to be doing in calculus later. All right, so I want to go over one other example because I feel like that was a little bit confusing. All right, so given this sequence, I would like you to sum that into infinity. All right, and the first thing that we need to do, we should know that it's geometric, right? So if we take the ratio of each term, we'd get 1/10, right, between each one of these. would be so 3 times 1/10 is 0.3, 0.3 times 1/10, that's 0.03, and so on. So this is our common ratio. Our first term is just 3. So we have a common ratio, and we have our first term. And that's really all we need. Right, so the sum of this entire thing up into infinity would be equal to our first term over 1 minus our common ratio and then it sums to 10/3. Okay, I want to stop there. I know that this infinite stuff is a little bit more confusing, but if there are any questions on your screen right now, let me know and I can address those. And then after that, we'll talk about the homework a little bit. Okay, so your homework is W12, and I'll put that into on campus here in a second. And it has to do with the sum of finite geometric sequences. So it has to do with this stuff right here. All right. And keep in mind, you got to be careful with the lower limit and the upper limit. But other than that, it's all about the same. Okay. So I'll leave this open for a couple of minutes. If you have any general questions, you can ask me here. Otherwise, I'll start a meeting in Teams for any other specific questions. since there are no questions, I'll end this and I'll start a meeting on Teams. If you have any specific questions, I'll answer them there. All right, so I will see you there.